Hello everyone. For today's video lecture, we're going to be talking about moment integrals. So first of all, what is a moment integral? A moment integral, as the name implies, is the general concept of using integration to determine the net moment of a force that is spread out over an area or volume. So the integral of the moment, which is generally going to be the integral of the force times distance, except in this case, the force is not just kind of one particular value. It's going to be a force function, and so that force varies with distance. So with all of this, so imagine we're going to build up to conceptually to that integral. Imagine we have a beam with a single force acting on it as shown below. So we've got a beam, it's a cantilever beam, it's got a 50 Newton force on the end of a 10-meter beam. All right, calculating the moment for this is generally going to be force times distance. So the moment about point A, force times distance, it's 50 newtons times 10 meters. We'd have 50 Newton meters as the magnitude of the moment, actually be a negative moment because it'd be clockwise rotation in this case. So that's all well and good. That's the moment of a single force. If we have a number of different forces acting on the beam, we can find the total moment exerted by all the forces by summing them all up individually. So the sum of moments about point A is going to be force 1 times distance 1 plus force 2 times distance 2 plus force 3 times distance 3 and so on. So it'd be 60 times 5 plus 30 times 7 plus 50 times a total of 10. Simply add all those together and we'd find the overall moment. So moment integrals, we take the one last step. So if we imagine something, a distributed force is basically an infinite number of very small forces. We're going to do that sum, except we're going to replace it with an integral. So here is our distributed force, and we are going to sum the forces by using integration. So the integral, the moment integral about point A, is going to be the force function f of x. So it's the mathematical function of the force at any given value of x, any given distance, times x. So force times distance, I've got a mathematical function. I kind of multiply those two together, take the integral, and the sum there would be the moment integral of that piece. So we've got different types of moment integrals in all of this. That's the general concept of the moment integral. But it's a broader concept than that as well. So the idea of using integrals to sum up moments, also we can have the resistance to moments, resistance to bending, resistance to torsion, resistance to angular accelerations, is the idea of the moment integral. So I'm going to use the term moment integral to kind of be all-encompassing in all those pieces. And we've got lots of different types of moment integrals. So there's a number of different distinguishing characteristics of these moment integrals. We can do it in 1 dimension, 2 dimensions, or 3 dimensions. So that depends on our problem. We kind of use the context to determine how many dimensions we need to use. So our force was actually spread out in 1 dimension before, so it was just spread out over a kind of a single line along our beam. We can also have forces spread out over a surface, that'd be 2D, or forces distributed through a volume, like a gravity force, is going to affect every part of the body, and so that'd be a 3D moment integral. So in addition, we can be integrating various types of functions. So we've got force functions, like we just did. We can actually just integrate the area or volume that's going to be relevant to the resistance to bending or torsional moments, or we can integrate with respect to the mass. And so the mass is also going to be resistance to moments, and it's going to be resistance to angular accelerations that we have. So we can integrate any of those things in any of those 3 dimensions. We can have first or second moment integrals, and so first is just force times distance. The second would be force times distance squared, or area times distance squared. If the distance is squared, it is a second moment integral. And finally, we're going to have rectangular or polar moment integrals. So either we are kind of moving left to right, up, down. If we're moving in kind of one direction, that's a rectangular moment integral. If we are radiating out from an axis, that is going to be a polar moment integral. And so those are a little more complicated, but definitely have some uses in many cases. All right, so those are the different characteristics, and we can potentially have any combination of the characteristics above, but only some combinations are going to have practical purposes, practical uses in engineering mechanics. All right, so what are those uses? What are the uses for these moment integrals? So we have many different uses in mechanics that are spread out across statics, dynamics, and strength of materials. And we can use these to calculate the net moment and the equivalent point loads for distributed forces. That's the most straightforward one. Is the literal moment integral in that case. We can also use it to find the centroid or center of mass for some body. So that is again going to be a first moment integral. We're going to be using centroids, or sorry, the areas or volumes or masses in place of our forces. We can determine a beam's resistance to bending if we look at the cross section and do the second area moment integral. We can determine a shaft's resistance to torsional forces or torsional moments if we look at the cross section of that shaft and determine the second area polar moment of inertia. And we can determine a mass moment, or the mass moment of inertia for a body, the I value, which is a shape's resistance to angular accelerations. So all of these things are based on moment integrals. It's a topic that kind of comes up over and over again. They're very different uses, but they're all kind of the same math underneath. It's that force times distance, or area times distance, or mass times distance, or distance squared, and so on. All right, so how do we determine the moment integral? So there are various methods. Generally, we're going to be using two methods to calculate these values. So number one is integration. We can actually do the math, determine the mathematical function for the force, for the area, for the mass. We multiply that by the distance, so force times distance, area times distance, or distance squared. And then once we have that mathematical function, we integrate. So that is kind of the brute force method. That is the base method for these moment integrals. It's just actually do the math. Method two that we're also going to be learning is the method of composite parts. And so for the method of composite parts, we're going to break up your force or your area or your volume into pieces. We're going to look up kind of predetermined integral values in a table. So those are available as a resource with the mechanics map. Also with most textbooks, you're going to have those tables available. And then you combine those values, those kind of predetermined integrals, to find the final solution. So generally, integration is the brute force method. It's going to work for anything as long as you've got enough time and enough mathematical ability to make it work. Method of composite parts is going to be a lot faster. It's going to be a lot less integration, but it is going to be limited by the tables you have available. So you cannot do everything with composite parts unless you've got a table that is infinitely large and has every kind of combination of area and volume that you possibly could have in your part. All right, so that's all we have for today's video lecture. Thank you for watching, and I hope to see you again.